So, sometimes I'll talk to you, sometimes I'll talk to the camera, right? Right, people at home? Sometimes I'll talk to you, sometimes I'll talk to them. Okay, so quick review, couple minutes. Just what we said already is that we can have like motion diagrams, and if we call it a motion diagram, this is being picky, it's kind of like shows an actual picture of the car on it. All right, and what we use in here most of the time is called a particle model, which you just make a dot, and the dot represents the car. Does that make sense? All right. Another thing, let's do a particle model of a car speeding up, a car accelerating. All right, we'll make a line. Now, if it's accelerating, that means initially it's going slower, and then if we map it out where it was every second, then the dots get further and further apart. The distance between these dots represents the amount of space covered, and then you have to assume that these dots are represented for a car is like maybe every second. So you're imagining that there's a camera here. That's an old-fashioned camera, okay? You're imagining there's a camera, and it's taking a picture of the car one time every second, right? So if you see these dots getting further and further apart, this thing is accelerating. This would be a particle diagram of maybe the beginning of a race. Does that make sense? Now, another thing we could do is we could throw arrows on here. And the arrows are representing velocity, okay? And there's a direction on there. And they're not truly vectors unless we put a number on these arrows. But what can you tell me, Darius, about the quality of these arrows? The quality.
They're moving in the same direction.
They're all going in the same direction, right? They're all going in the same direction, but compare the arrows to each other. How do they represent the increasing speed? What is it about each arrow?
They're moving to the next one.
They are, but it's easier than what you're doing. What do you think, Ryan?
They're getting longer.
Yeah, that's it. Yeah, it's like so obvious you weren't saying it. Yeah, they're getting longer. So the longer arrow, qualitatively is representing a greater speed, right? A greater velocity. Okay, so this is how particle diagrams work. And then the other thing that you should have learned already is very simply that if you look at your speedometer, okay, a really popular speed is 55, right? Very often that's the speed limit on a two-lane road. 55 what, John? 55 what?
Miles per hour.
Yeah. And miles per hour are garbage as far as we're concerned because we use the metric system, right? But I'm just making a point that you've heard this term 55 miles per hour your whole life. Now, if you look at the formula for velocity, it's given to you in the statement 55 miles per hour. Velocity is equal to distance over time. So this is miles per hour. Does that make sense? So this 55 mph is representing this formula. What was that car's velocity? 55 miles per hour north, or 55 miles per hour south. For it to be velocity, it has to have a direction, right? If there's no direction, you just call it speed. But don't worry, that's not like a test question, okay? So we wouldn't talk about miles per hour. 55 miles per hour is probably something like, I don't know, 70 kilometers per hour. Well, if we were gonna measure the speed of something, especially like a little remote control car, which we were about to do, we would give that speed in meters per second. And that's still distance over time, right? Okay? So the last thing I'll tell you is we went out in the hall, and on the last video we had the car, and we had these little units already given to us in the hall that are the tiles, right? So last week, we just did TPS, tiles per second, because we can see those tiles on the floor. Does that make sense to everyone? All right, we did that, and then we did a little worksheet. And that was it. That was your whole class. So there's your review.